Yeah, in the last class, last lecture, I noticed that I made a mistake here. So this MQ, this will knock off this M, right? So here it will be Q, right? This delta MQ will knock off this M. So this is the component of, this is the divergence of a second order tensor. So sometimes, sometimes we need to express these gradients in a matrix form. Okay, and the most often that we need to do this is for the gradient of a vector. So remember, the gradient of a vector is a second order tensor. Its elements are ui comma j. So the elements of gradient of u are ui comma j, and they are arranged in this way. So this is ui I equal to 1 and j equal to 1, 2, 3 in the first row, I equal to 2, j equal to 1, 2, 3 in the second row, and so on. So this is how they are generally arranged. They have to be arranged, um, which is a little bit counterintuitive because you would have expected this row to be the column, but uh, this is how it needs to be done, and I'm not going into why this needs to be done like this, but please remember that this is how it is done. Whenever you express this as as a 3 cross 3 matrix, this is how you should do it. This is how you should arrange the components. Now divergence of u is a scalar, and that you can immediately see is uk comma uk. That's the divergence of u, and that you can see is the sum of the diagonals of this matrix, del u del x1 x u2 x2 u3 x3. That's the sum of the diagonals, and that's equal to trace of the gradient. So the trace of the gradient gives you the divergence of a vector. This is the matrix representation of the divergence. This is the representation of the second order tensor. That is the divergence of a vector. Okay, so there's one more thing that we need to do, which is a very important theorem that you might have learned in other courses, in your basic calculus courses, which is called the divergence theorem. What the divergence theorem does is it helps you transform um, integrals over a volume V into integrals over the surface S, or vice versa. To do that, there are a few things that are necessary. Consider that I have a vector field or a tensor field uh, which are functions of position. So I have a vector field which is a function of position. That means all over this space, this vector field is defined. And I have a second order tensor field which is again a function of position. So as I change the position, this tensor changes. So I have a tensor field that is defined in this whole volume, whole domain. Within the domain, I have a volume V, which has an outward normal at any point given by n. So this is the volume V, and the red thing is the volume V, and ds is a small surface element on volume V which has a normal given by n. Okay, this is an outward unit normal. It has to be outward. The word outward is important here. So the Gauss divergence theorem transforms a surface integral on the surface of this volume S to a volume integral, and we know these statements. At least we know the first statement. We know that u dot n ds, this is called the flux, and integrated over x, S is the total flux. So the total flux from the through the surface, which means that inflow minus outflow minus inflow on the surface, is equal to the divergence of u over the volume. So this is a surface integral which gives you the flux over the surface, that is equal to the divergence of u over V. This you might have learnt in your mathematics courses as well as in your fluid mechanics courses. So we can actually take this to a second order tensor as well, and we can say that this is the flux of a second order tensor. So T times n is a vector, T is a second order tensor, so T times n is a vector, and that is equal to the divergence of T taken over the volume. So this is actually three equations because T times n is a vector and it has three components. Divergence of a second order tensor is also a vector, it has three components. So basically this vector equation hides three scalar equations, whereas this is a vector equation, but it is only one scalar equation. This left hand side is a scalar and the right hand side is also a scalar. Now these statements can be written in indicial notation, and this will be very useful for us. So the way we will write it is okay, the way we will write it is like this. So what we have in the first statement is over n you have u dot n ds, and in your fluid mechanics courses you might have learned that this is applied to when u is the velocity, and then this gives the total flux from the volume. So this is into divergence of u over v. So the way we can write it in indicial notation is component wise. This will be uk nk ds will be equal to volume. Divergence is del xm em dotted with, let's say, u p ep dv. So this will be equal to em and ep give you delta mp. M will knock this off. So del up del xp dv. This is what the indicial notation form is. And what I can do is I can not use p here and use n here, right? So this is what I can do. This is a p was a repeated index, so I could have used n. No, I have used k on the left hand side, so I can use k here. Okay. So now, if I'm given this relation, so suppose I'm given this. If I'm given this, the quick way to convert it into using Gauss divergence theorem is look at what is here. Here you have nk, and if you have nk, just bring in xk here and get. So whatever is the index of the normal, that becomes the index of the del x here, and this is same as what we showed here, right? This is same as what we showed here. So a quick way of applying divergence theorem is that whatever is the index of the normal will become the index of this. So if you are given this expression and you have to convert it into surface integral, and you would just write, you will just see what is the index of k, that would become the index of, so you will write uk nk ds directly. You will use the index of x to make it the index of k in the surface integral. Okay, so so we can do this actually for other quantities as well. So we can use this to do it for let's say for a second order tensor as well. So moment I see second order tensor surface integral, let's say a n ds. So I have a surface integral like this, components of which are written as a I j n j ds. So this has three components because this is a vector. It is three components. The ith component will be written like this, which immediately we see we have nj here. We have to convert it into a, so we will write a volume integral, which is where the x has the same index as the n, and this will be your volume integral. This will be the conversion of this surface integral, which represents the ith component of this, into a volume integral. Okay, so this is the trick that we will use while using the divergence theorem. Whatever is the index of the normal in the surface integral will become the index of x in the volume integral, and derivative will be with respect to x of that, x with that index. Okay, right. Now if we take t equal to phi I, then this is what we will get. I is the identity tensor. You can use this relation for second order tensor. Put t equal to phi I, that means aij equal to phi delta ij. You can put it in and you can see that this is what you will get, which is the divergence theorem for a scalar function, which is the divergence theorem for a scalar function phi. And it's a specialization of this statement that we have, and it's sometimes called the Green-Gauss Ostrogradsky theorem. Don't have to remember, we'll always call it the divergence theorem. And here also you see that you have Ni here. You have Ni here. So when you convert it into volume integral, you will get del xi. So that's what we have got, and whatever is here will remain on the top. So our um, basic way of remembering this is what is the index of Ni, that becomes the index of the del xi for the volume integral. That's and vice versa. If you have del xi here and you want to convert it into a surface integral, you look at this index and put that as the index of the Ni in the surface integral. Okay, so this is all about tensor calculus that we had to do, and we'll have a test on this. We'll have a small quiz on this, so you have one this week to study this up. I'll upload all the notes and the recordings. So see you next week then.